Okay, let's go ahead and get started. So this is the session for using large language models to answer difficult science questions. And to start off, with a show of hands, would anyone be able to tell me about modified Newtonian dynamics? One person? Two people, maybe? Okay. What about the reactive Leidenfrost effect? Anyone know about that? One person? Two people? Okay. And I imagine maybe two more hands will show up when I ask about X-ray pulsar-based navigation. And if I'm being honest, I don't know about any of these, but I worked on a team that built an LLM system that can answer about 90% of these correctly. And so who am I? My name's Nicholas Broad. I'm a machine learning engineer at Hugging Face, where I help enterprises and startups to best use open models and open libraries to incorporate that in their production workloads. And what is Hugging Face? It's a goofy name, but we've been around for a few years, and our goal is to be the GitHub of AI and machine learning. And right now, I took this screenshot just yesterday, showing that we have nearly 600,000 models available freely to use, with some of the biggest tech companies and startups sharing state-of-the-art models for text generation, for image generation, for document understanding, and a whole bunch of other tasks as well. And so you can see some familiar names on the trending list of the models. So you can see Google has shared the Gemma models recently. Those are pretty popular. Mistral is also very popular. They share very powerful LLMs, but you might also notice that there's some image generation models from Stability AI as well. And it's not just models, there's also a wide range of data sets as well. So we have over 130,000 different data sets for a variety of purposes. Recently, it's been mostly about training LLMs, but of course there's image data sets, there's audio data sets, there's tabular data sets, and lots that's shared by the community and by research. And then one of the most popular areas of Hugging Face, the website, are the spaces. And so these are applications where you can show off the work that you've been doing, the research that you've been doing, a model that you built, or maybe just a fun demo. And so here's one showing off the new Commander model from Cohere, and so you can interact with a state-of-the-art chatbot. We have one where you can generate your own comic book. We have some where you can modify your face with different styles and do funny things. So here I am modifying a photo of myself to make me look more like Tintin-style art. And please check us out at hf.co. It's just 4 letters. We have a lot of open source libraries as well as models, data sets, and spaces that are always showing off the great work that research labs do as well as the community. So back to the talk. As a general overview, I'll be talking about the competition of where this was taken from, the game plan that our team decided to go with when deciding how to approach this task. And then the main topics will be data generation, retrieval augmented generation, and modeling. And like I said on the last slide, the main things that we'll cover today: how to use LLMs to generate data, how do you use open source libraries like Gradio to analyze the workflows that you're using, how can you train multiple choice question answering models using Hugging Face, how best to use retrieval augmented generation, and what are the best tools to do all of this with. So as a bit of a background, this was part of a Kaggle competition, and Kaggle is a company owned by Google that hosts a wide range of competitions throughout the year, mainly focusing on data analysis, data science, machine learning, and AI. And so this one was focused on using LLMs to answer multiple choice science questions that are pretty difficult. So it ran last year from July to October. It had about 3,000 participants and over 2,500 teams. And so my team placed 6th out of all of them. And so they asked me to talk about our approach at this conference. So I'm very grateful to be teamed up with great people. So even though I'm here presenting, the work is the culmination of a lot of people and collaboration. So what did they actually provide for this data set? Well, they actually only gave us 200 questions. Each of them have 5 possible answers. And they said they used GPT 3.5 to create these questions and answers by referencing some science articles in Wikipedia. And as an example of the types of questions and answers that they give, there's this one here on Newton's second law. And so most of these are highly technical, very specific, that I would imagine most people wouldn't be able to answer correctly. And so that's what they provided as training data. And then they said at test time, you'll have 4,000 of these to answer. Again, 5 possible answer choices. And again, it's produced in the same manner where we have GPT 3.5 creating both the questions and the answers. And so as part of this competition, you do have some limitations because you have to use the Kaggle runtime. And so all the hardware that you got was 2 T4 GPUs, which have only 15 gigabytes of VRAM each. They're supposed to have 16. Don't ask me where that last gigabyte went. The CPU doesn't have that much memory. It's pretty weak. And you have a total of 9 hours to do all 4,000 of those questions. And so on average, that's about 7.5 questions per minute, which is pretty slow. But when you start running multiple models and have a more sophisticated approach, and you want to go for the best, you try to use that 9-hour time limit as best as you can. And then, of course, there's no internet access when you're doing this, so you can't just make calls to ChatGPT. You have to use a model of your own and have it run offline. And so our game plan was to first generate more data because we realized like 200 examples isn't much to go off of. Using an open source model depends on having a large amount of high quality data. So the first objective was to generate thousands of more examples so that we can fine tune an open model and boost the performance in that way. We also realized we should go with a variety of different models and approaches so that we have a diverse ensemble when we're doing inference. And then the next thing we also realized is that because these questions are very specific and technical, it'd be useful to add helpful information into the context window of the model while you're asking these questions. They'd be extremely hard to answer without any context. They're still pretty hard to answer with context, but that context is going to be super useful. And then after this, we're going to combine as many models together as we can, just averaging the predictions together, and hopefully that'll work out for the best. And given that we got 6, I think it did work out pretty well. So starting with the first part on data generation involved crawling through Wikipedia. So we knew they said they used Wikipedia for their sources, so we thought we should do the same exact process. And so there's 2 reasons why we wanted to use Wikipedia to crawl through and get chunks. One is so that we can make more questions and answers to train on. And 2 is so that we can use those chunks at inference time as useful context. And so Wikipedia has a portal on science with a lot of categories, and each of these categories is broken further into subcategories. And so we crawled through all the pages that fell under the science category, and what we got was 500,000 pages turned into 3 million chunks. And so when we're working with embedding models for retrieval, you don't want to pass too much information at once. And so that's why chunking is necessary for those really long articles that have a bunch of different sections. And so we found that a chunk size of about 7 to 12 sentences worked best. And we also made sure that any equations were converted correctly to MathJax and LaTeX. So part 2 of data generation is then creating a training set that you can train a model on. And so for this approach, we would show the model a passage from the crawled corpus of Wikipedia texts. We give it a prompt telling it, please make a multiple choice question about this passage. And we used a variety of models to do so. And so the exact prompt that we found best was the following. We said, you're an excellent professor, and you want to generate a multiple choice test for your students. This is an open book test where students are supposed to combine science text snippets with their general knowledge via critical thinking, reasoning, and logic to answer the questions. In the following, please leverage the provided text as science knowledge and generate a multiple choice test with 3 questions. Each question should have 5 choices, and only one of them should be correct. We would then insert a science text in there, give it a little template of how we wanted to format the questions, and we were good to go. A few things that I want to point out is that the first thing we did was give it the persona that we thought would help it do best. So we said, you're an excellent professor, hopefully guiding the model to make smart decisions and come from the perspective of a highly trained individual. We also told it to use critical thinking and reasoning to try and make the questions as complicated as possible. Maybe not complicated, but as difficult as possible. The other thing is that we told it to generate 3 questions, and this is a bit of a trick to have it be more efficient and cost-effective. So instead of each context creating 1 question, now we have 1 context creating 3 questions. So a little bit faster, a little bit more cost-effective, and we didn't see any issues when generating data that way. And so why use different LLMs? We used a mixture of proprietary ones, like BT and Claude and Cohere, and then we also used open ones like Llama and Falcon. And each of these was trained on slightly different data, slightly different methods. They're all slightly different sizes. So they're all going to have their own style and bias. And we knew that the competition used GPT 3.5, but we didn't know how they prompted it. And so we thought, if we can create a diverse set of questions, our model's going to generalize better, and we're probably going to be able to do better on this test set. That was the primary reason. And then the secondary reason was that some of us hadn't used some of these models, and we're just curious to see how they would compare. How do these open models compare to the state-of-the-art proprietary ones? So all told, we generated about 60,000 of these multiple choice questions, and not all of them are equal quality, and I'll touch on that next. And so when you're doing this data generation process, some of them are just pretty bad and confusing. And so this one's on continuous and discrete symmetry and math, and all of the answers are so similar that none of the models could really predict this correctly. And so one warning I would say is that when you're generating data, there is a risk that the model's not going to do a very good job, that you are going to make these really confusing questions that are probably going to hurt the model when you're training on that data. The other thing that we notice is that sometimes the model will inject its own knowledge into the question. And so in this case, the correct answer wasn't actually present in the context that was provided, making it so that the models couldn't understand how to approach it. And so again, generating data, there is the risk that the model will inject its own and potentially incorrect knowledge. And so this is where Gradio came into play. Gradio is an open source library made by the Gradio team, which is part of Hugging. And it's a very easy way of building web applications to off models, but it's also a way of analyzing data. And so within 50 lines of code or so, I had this interactive app that I could share with my teammates to quickly look over the questions that the models were struggling with. And so we used a k-fold validation approach, and we compared all of the out-of-fold predictions across multiple seeds and questions that multiple models could not get we would throw them out of the training set because we realized that these were bad, low-quality samples, and we should not train the model on it. And this did help a bit, and it was an easy way of assessing the quality of the generated data. And definitely a word of advice when you're in these complicated systems is that error analysis is very important. Looking over what your model cannot do correctly is enormously impactful for figuring out how to boost the performance and figure out the next steps. So that's the section on data generation. Next part is on the multiple choice MCQ model training. So we went with 4 different models, and each one used slightly different approaches, so we'll cover that now. So the first is dBERTA v3 large, and if you've heard of BERT, dBERTA is basically the improved version of BERT. It's noticeably better in nearly all regards. It runs a bit slower, but if you're doing any sort of classification task, it will always outperform BERT, usually by a large margin. Unfortunately, it goes a bit slower and it takes more memory. But if you're trying for the best accuracy, there's no substitute for dBERTA v3 large. Fortunately, there's a lot of size variance. So there's a base size, there's a small size, there's even an extra small size. So you can think about the balance between model quality and model speed. And this model is available freely on Hugging Face, and I would strongly encourage you to check it out. And so we actually went with 3 different ways of using this model for classification. And I know some people wouldn't consider this a large language model because it's only 350 million parameters. And in today's times where things are 7, 30, 70, over 100 billion parameters, this is tiny in that regards. But it's still very powerful, and oftentimes it'll be easier to train, cheaper to deploy. And for classification purposes, it'll be just as good as an LLM. So the first way we use this is basically a pairwise classification. We would provide the context, we would provide the question, and we would provide one answer. And the model is supposed to predict a score for this pair. And so if there's 5 answers, we have to do 5 different forward passes. But this does work pretty well. And it's supposed to produce a score of 0 to 1. I know my scores aren't from 0 to 1. That's because those are the raw logits. But if you take sigmoid, softmax over all of them, boom, now you've got 0 to 1. And this approach here is very straightforward to do within Hugging Face. There's a model class called auto model for multiple choice answering. And it's very straightforward to do. The second option we went with was more of a span-based classification approach. So now instead of doing 5 different passes for each of the answer choices, now we're putting all the answers into the context window at once. And so the advantage of this is that the model can compare each answer to all the other ones, and you're only doing 1 forward pass. The disadvantage is that your context window just got a lot longer, and there is some position bias. So if you take the same 5 answers, shuffle the order around, you'll get slightly different answers or scores for those answers. And so basically, if answer A is if those are the tokens from index like 100 to 200, we would take the output representations of those, average across that whole answer, and then pass that through a classifier to decide if that's the best answer. And so the good thing about this is that each answer can be compared to the other ones, and you're using a pooled representation of that answer to classify whether it's correct or not. And then the final way we used dBERTA was by doing a single token prediction. And this is essentially what LLMs do. And so even though this model wasn't trained to do text generation, all we needed to do is predict one token. And so it still was able to do that pretty well. So if you're familiar with masked language modeling, this is basically masked language modeling with a single token at the end. And so again, this is one forward pass. We have all answers in the context window at once. And then we use the representation from that masked token to predict one of the letters A, B, C, D, E. So for all of those approaches, they all did roughly the same. But because they were slightly different approaches, using all of them together produced a more robust approach. The next approach I want to talk about is using LLMs like Mistral 7b and Llama 7b or 13b. And so this was trained using QLoRa on A100s. QLoRa is an approach where you can train really big models on really small hardware. Yes, I used A100s, but you can actually train these on models or GPUs as small as 16 gigabytes. Probably it'd be better if you use something like 24 gigabytes. But it really made it accessible for people to fine-tune these really big models and still get good performance. And so with these models, again, there's a couple different ways to approach it. We went with two very similar to what we did with dBERTA. The first one is like that pairwise comparison of you have the content, you have the question, you have a single answer, and you're producing a score for that pair. The cool thing about these LLMs is because of their attention mechanism, you don't have to rerun the context in question multiple times. You can cache the key and value representations and then just run the answer, the new answer for each option. And so that actually saves a lot of time. So you're not doing 5 full forward passes. It's like 1 and then a small fraction for each of the answer options. And because the context is usually where the bulk of the tokens are, it's a way to make it a whole lot faster. And then the other option is passing everything through at once, where you have context, you have the question, and then you have all the answer choices. And this is nice because it's just one pass, one forward pass. The disadvantage is that if you have really long answers, your context length increases a lot, which can take more time, which can take more memory. And when you're working with these really large models, that might be a limitation. The last one I'll mention is T5. I think this is an underrated model that's been around for a while. And this one's 3 billion, so it's maybe a medium language model, not a small one, maybe not a large one. And it's a different architecture that doesn't get a lot of attention these days. So it's technically a encoder-decoder architecture. And so the way you approach this is that you're passing the context, the question, the answer choices into the encoder part of the model. It'll create a representation. And then through cross-attention, the decoder will generate text based on those representations. So very similar to how decoder-only LLMs like Mistral or Llama work, but you get slightly more robustness when you're combining all these different types of models. And so that concludes the portion on training multiple choice question answering models. The next part is on training embedding models. Because at inference time, when we get a question, we have to find relevant contexts. And so if you have an embedding model, you can create an embedding for all of the documents, all of those Wikipedia articles, and then you can compare it with the question that you're trying to answer. And so you want to pull up the most relevant documents for that question. And so we thought, hey, let's fine-tune an embedding model so that we get the best performance possible. But what I would say is that there's a lot of really high-quality embedding models, and if your domain of your text is very generic, you can get really good performance like straight out of the box, straight from the Hugging Face Hub. And plenty of the top teams were able to do just that. They didn't bother training embedding models, and they still got pretty good results. And so the idea behind this is that that data we generated before, where we have a question, we have a context, works perfectly here. So with an embedding model, we're going to create a representation for the question, we're going to create a representation for the context, and we're going to train the model so that the cosine similarity between matching and relevant question and context is high. And then for context and questions that aren't relevant, it should produce a cosine similarity that's really low. And so when you're working with a large batch of examples, you're putting positive pairs together, and then you're assuming that the everything else in the batch is considered a negative. So this is a very straightforward approach, a bit naive, but it still works pretty well. And it was able to boost our scores a little bit. And so maybe you're familiar with sentence transformers. It's another library that's out there that's built heavily off of Hugging Face transformers. And Hugging Face is actually maintaining sentence transformers now. There's a lot of convenient scripts in the sentence transformers repository for training embedding models like this. And on Hugging Face spaces, we have a lot of leaderboards, and one relevant leaderboard for this is the Massive Text Embedding Benchmark Leaderboard, MTEB. And this is where a lot of the embedding models on the Hugging Face hub show up, and you can compare their performance across a lot of different tasks. Of course, I would say just focus on the average score across all 56 different data sets. That's probably going to be most representative of the quality of the model. Now, recently, a lot of LLMs have shown up at the top here. So we have models that are 14 billion, one's even 93 billion parameters. And I think those are more of like research novelties and not really useful for most people. At the time, we used some of the best ones out there. So one called BGE, one called GTE, and one called E5. And these are much smaller. These are like 100 million parameters. And very, very fast, very useful for doing retrieval and semantic search. Now, the second part of doing retrieval and finding the most relevant context is involving a re-ranker. So typically in retrieval, you'll have a fast step that gets a bunch of candidates, and then you'll have a slow step that narrows down those candidates to the best options. And so the embedding model, comparing the embedding representations and doing cosine similarity, that's the fast step, and so you can get the top 50 or 100 results from that, and then you can pass it into the re-ranker model. And so the re-ranker is going to be better at judging whether it's a good fit, but it's much, much slower because every context and question has to be compared one at a time. And so we use dBERTA v3 large for this as well. We would pass the top 50 or so results from that embedding lookup, and then we would see which ones have the best score from the re-ranker. And the top 3 would be the ones that actually made it into the context window when we're doing inference. And again, we can use the generated data, the pairs of context and question, as positive matches, and then a random pairing as negative examples. You can boost your performance a bit by mining hard negatives for the model where the context is similar but not quite right. And the reason this is useful is because the model will better be able to figure out what the correct pairing is. So as an example, if I have an article about the reactive Leidenfrost effect, and I have a question about the modified Newtonian dynamics, very different subjects, very different words. But if I choose a topic that's a little bit similar to the question in mind, now the model has to work a little bit harder to make sure that it's a good fit. In terms of evaluation, because they only gave us 200 samples, we knew that we would have to come up with our own way of validating these. Moreover, we knew they were heavily skewed towards physics, but the science section of Wikipedia has biology, it has chemistry, there's even like history of science sections. sometimes philosophy and psychology and other areas of science would show up. So we didn't know exactly what we would be tested on. So the idea was to have a diverse representation of all the potential topics. So all told, we used about 5,000 different examples to validate our models on, and use the highest scoring ones and submit to the competition. Now, when we're retrieving context, oftentimes people talk about using vector databases. And there were some people who did use vector databases, but we found it easier to just do a simple dot product matrix multiplication using a torch tensor. We only had 3 million chunks, we only had 4,000 texts, and the multiplication between that is actually very fast on GPUs. So we didn't want to bother with the headache of installing extra packages and dealing with those dependencies. So it was just a very straightforward way of doing that lookup and finding those results with the best cosine similarity. Now, I would say that if you're working with a production system and latency is very important, and you have documents on the order of tens of millions, hundreds of millions, billions, yeah, I definitely recommend using a vector database in that case. And so in the end, when we were combining these models, is a very straightforward approach of averaging all of the predictions together, and we found that worked pretty well. And of course, the more models you can use, the more different those models are, the better your results are going to be. And the last thing I'd add is that we actually did manage to use a 70 billion parameter model within this competition. Someone else had graciously shared their technique for running it in this very restrictive environment. And it's kind of impressive because a 70 billion parameter model is 140 gigabytes of weights, and we were running it on about 30 gigabytes of RAM on the GPU. So the way around this is to go layer by layer, loading that layer onto the GPU, taking that intermediate value, storing it, unloading those weights, loading the next layer, and you do this for all 70 layers or something like that. It's very slow, it's very inefficient, but these models are very good. And so what we found was that we didn't have time to run it on all of the samples. So let's just take the questions that we're getting variance from and pass that to the most complicated model, the most sophisticated model. And hopefully that will be the best judge for those really hard problems. We didn't have time to fine-tune a 70 billion parameter model. Using QLore, it would be possible. Within a few hours on A100s, you wouldn't need that much data because it would learn very quickly. But luckily, there's a lot of pre-trained instruction-tuned models on the Hugging Face Hub, so we just used one of those, and we're able to boost our scores a bit in that regards. The last thing I'd really add is that the power of context should not be understated. So these models, they're pretty good, but you give it more context, you give it background on what this question is really about, and it significantly improves the performance. And so this is what retrieval augmented generation is all about. You can just insert in the information into that context window, and these models will do a whole lot better. And so here is the somewhat chaotic diagram of how our final model pipeline look. So if we start in the top left, if we have an incoming question, we would pass that to the embedding model to create a representation. With that embedding, we would compare it with all of the embeddings from the Wikipedia articles that we scraped. And so those Wikipedia embeddings had already been calculated beforehand. And so we would just look up the most similar ones, trace that back to the actual texts, pass those texts to the re-ranker. And so we'd take the top 100 from the embedding lookup, pass that to the re-ranker, and then we would take the top 3 after the re-ranking phase and pass that to all of our models. And that would produce the predictions, and we would average those out. And something I don't have listed here is that 10% that we use the 70 billion parameter model for. So a lot of steps to answer a question about science. Now, after saying all this, I'm sure many of you had this thought while I was talking, like, is this like a realistic approach, or what's the value in doing something like this? And yeah, I'll be completely honest, like multiple choice, especially these types of questions, is like a pretty academic task. I know of many people who work at like companies that are dealing with multiple choice questions, especially about science like this. And on top of that, they give you 9 hours to complete all of this. 9 hours is a pretty long time. Even if you're doing some batch process like overnight, you'd probably want it to be shorter than 9 hours. And then the last aspect is that the GPUs we're working with are kind of old, and so they don't allow you to use some of the latest technology. And so maybe you've heard of something called flash attention that makes LLMs run a whole lot faster. And all of the approaches we used didn't really do generation. We're more just doing classification. And it'd be really interesting if we had better hardware so we could do generation, so we could use more advanced techniques like chain of thought reasoning, where we're asking the model to think step by step to answer these. That could help produce better scores. Or even just working with ensembling the chain of thought predictions together. Overall, like these models are too big, the hardware is too limiting to actually use generation to get a lot of to get the answers for something like this. We had to just go with a basic classification approach. But what I would say is like Kaggle's a great place to learn. It's a great place to explore all of the open source libraries that Hugging Face offers. And so the learnings about data generation, the learnings about doing retrieval augmented generation and working with these models, I think all of that is very valuable. And it's fun to compete in things like this, and I've learned so much doing Kaggle. I definitely recommend, if you're curious, try it out. There's a lot of cool people who share interesting ideas, and hey, maybe you'll do so well that you win some prize money. So what were the open source libraries that I used for this? I'm really emphasizing all the Hugging Face ones because these ones are really crucial. So Hugging Face Transformers, which is the most popular library, this is where you have access to a lot of those pre-trained models, and there's a lot of convenient abstractions to make modeling very easy. Accelerate is a convenient library when you're doing distributed training. So if you're working with multiple GPUs, very easy to get going in that regards. Datasets, very useful for processing data. PEFT, which stands for Parameter Efficient Fine Tuning. That's where you can use LoRa or QLoRa. Bits and Bytes is technically not a Hugging Face library originally, but we're now maintaining it. So it's like an honorary Hugging Face library. And that's where you can utilize quantization for LoRa. And then finally, Gradio, very useful for building out visualizations and quick applications. So that's the end of the talk. So thank you for sitting through it.